So looking at this problem from a different perspective, initially we thought about the number of samples we need to approximate a function that will nicely solve our problem or to fill a representation space nice and evenly. Previously looked at that and concluded that we need 10 to the power of 36 million samples to build simple image classifiers from our iPhone images. So looking at from a slightly different perspective, this huge number has also other implications on how we design learning algorithms. So if we would design a naive multi-layer perceptron for this image classification task, then connecting everything to everything in a multi-layer perceptron, like here, this is a very simple one. It has 36 million pixels input from our iPhone image and only 100 hidden units to process this data. But that alone would mean that there are in the order of n squared parameter in there. So 36 million squared parameters in such a network. So this very, very small multi-layer perceptron with 100 units would yield 3.6 billion parameters. This is clearly much more than there are cats and dogs on Earth. So this parameter is this network is heavily over-parameterized and intractable, basically. We cannot learn something like that. We can't probably even store 3.6 billion parameters for one of these networks. Now one of the very early ideas to tackle this problem was to just not fully connect everything to everything. You can just leave out certain connections with some constraints or even randomly, and you will still achieve good results. And in fact, the early networks were all designed, the bigger networks of the early ones in the 80s were all designed like this, simply for the reason to make them trainable. So if we, for example, leave out a lot of these connections, for example, let's put in a constraint that these hidden units don't necessarily need to know everything about everything here and about the whole image, but probably only a local neighborhood, then we only end up with, depending how sparse our connectivity is, with k times n parameters. That's already better. It's much better than the order of n squared, but it's still k times 36 millions, for example. So still, there are lots of parameters, and one of the key ideas of deep learning and CNNs was really to replace this scheme with something much simpler and say, okay, let's assume that the weights across these layers here are shared. What does this mean? Well, it means that I can just use a fixed set of parameters here to connect them, constant numbers, which I can update through training, and then use the same again in the next, for the next hidden unit, and the same again for the next hidden unit. The only thing that changes are, of course, the input neurons here, but the weights here are all the same. So there, in this case here, there are triplets, right? There's a red, there's a green, and there's a blue weight. And it's the same red weight for this hidden unit, and the same green and the same blue one. So that way, I only need to learn a very limited number of parameters, and I become independent from how many inputs I have here, actually. So in this particular case, I only need to learn 3 constant parameters for this network. So I have reduced from the order of n squared to simply k parameters. And now suddenly, huge networks become trainable, because we only need to train a very, very limited number of parameters for the individual layers, for a number of weights, basically. Now, this is well motivated from natural signals like images and continuous sound signals, for example, because normally natural signals are self-similar. There are lots of pieces in a signal that look the same if you look at a microscopic level. So for example, in this image here, there are all these green boxes here. They are very, very similar, right? It's a transition from very dark to very bright. And it doesn't matter where I look on this table here, it's always dark to bright, dark to bright. So it's apparently a strong vertical edge in this image. And that can be represented by a very limited set of parameters. Same here for this textured area. So these textured areas here look very similar, right? So this can be another set of parameters, another set of very, very small filter kernels here. This texture looks somehow similar. These homogeneous regions here, funnily the forehead of her looks the same as the carpet, but it doesn't matter on a microscopic level for this box. They look pretty much the same, right? So I can represent that piece of the image with probably 3 by 3 parameters, which is good. So let's construct a very, very, very simple example. It's probably the simplest example I could come up with. And the task for our network is to detect a click, right? Just a steep signal, a temporal signal, which comes from left to right. And the task of the network is to produce here an output as soon as it sees a click. Now, of course, I can train a multi-layer perceptron for this, fully connected, everything to everything, and put the desired output here, and then learn all the weights through backpropagation, propagate the error until I have a network function that fits this task very, very well. So I can learn this, and what I will end up with is a weight matrix that's densely populated. So there are a lot of different weights in here, or might represent something different. It might even change depending on how I initialize this network. But really, I have to process all of those. So I end up with n squared parameters, or as already mentioned. I can do the same. I can do the same with sparse networks. So if I sparsify my network, and if I do it, for example, with this scheme where I say, this hidden unit doesn't really need to know what's happening here. It should only probably look at that part of the time window here. Then I end up with a diagonal matrix. It's still a densely populated diagonal matrix because all of these weights might be different. I can train this the same way as the multi-layer perceptron. I initialize these weights randomly. And then I use backpropagation, propagating the error back from the actual output to the input. Now this will work. It will do exactly the same thing. It will tell me as soon as the peak comes into my window. It will tell me that the peak is here, right? It won't do it with 100% accuracy, but it will do the job. Now, if I do this with shared weights, if I do this with shared weights where all of these pieces here basically are the same, then I end up with a sparse diagonal matrix with which I need to multiply my input window here. And this is now really nice because all of these diagonal elements here are exactly the same vector. So I only need to train these, and again, I do it the same way as I would train a multi-layer perceptron and randomly initialize these three here, and then apply it and run it in a forward pass, and then in a backward pass, I adopt the weights to an optimizer and backpropagation. And maybe surprisingly, but yeah, that works exactly the same way. So it works, it will fit a function that will do the job, but now only with k parameters, right? Here in this case, only 3 parameters, which is really a low number for the complexity of the task. Now, let's look in very, very deep detail what's actually happening here. And we need to make a few definitions here. I'll spare you the training pass here. So what I can do with this network is, because it's so simple, I can just manually define what the layers are supposed to do, right? So I'm not the optimizer, and what I say is that this hidden layer here has specific rules. It says if at least 2 of the 3 visible input units here if at least two of them are 1, so if the sum of all of these 3 is greater or equal to, then this should activate. So there's a summation here and some activation function that puts this neuron to 1 if at least 2 of these 3 input neurons are 1. And here is the same, and here is the same. So for all of these 4, these rules are valid. I can visualize this slightly differently, and I can say, okay, this represents not continuous. It's a Heaviside function, but this defines a function like this, which if you're honest, this looks pretty much similar to what I'm looking for here, right? It looks for this continuous function that goes from 0 to 1, right? It looks pretty similar. It's basically my filter looking for this function. And now my output neuron does something very simple. It just builds the average of the hidden units, and this will be the final output, the activation. And I'll plot the output here, so that you can see how the output signal behaves given the state of t, of our time progressing. So now if we let the time progress a little bit, so our first unit will be activated. It's not enough yet that this activates, no output. Now the second activates, our output raises slightly. The third activates, so the second hidden unit here activates, our output again rises slightly. Now we have all 4 here, not all hidden units activated yet, so our output again rises. And now if I have this fully in view, all of our hidden units will activate. Our output will raise to its maximum, to 1, and as soon as I go out again, the output will fall again. So this is quite interesting. Keep this in mind. So what we have done is we have defined a function that looked similar to our input. So a box function here, a box function here. And what we get out is an activation like this. Keep this in mind. We will need this in a moment to understand why this is actually a convolution of 2 functions. Now I say it again, in practice, these filter kernels here will be learned through backpropagation, right? So I randomly initialize these 3 weights here, and then they will be learned. And they might be many. There might be many of these, many different filter functions in one of these layers. So what I can do is I can layer up the layer and have here one, and here one, and here one, and here one, all learning different filter functions. Like in the image example before with steep gradient changes or homogeneous regions, all of them will be learned dependent on what is required to fulfill the given task, like a cats and dogs classifier, for example. So why is this called a convolution? So if I write this in more general terms, what I actually do is I build a sum of our input and use the previous weight to sum this in. So multiply our input with the previous weight and then sum that up. So with that I pass from left to right. It's really like a sliding window here. And if you look closely, so you're probably familiar with these formulations. If you look closely, cross correlation looks pretty similar. So cross correlation, where I compare one function with the other function, is pretty similar, except that I look one step to the right to make this comparison, right, in the weight matrix. Now this is quite interesting, because if you compare this to continuous function signal processing theory, then this is equivalent to the convolution of continuous functions. So the whole idea of convolutions is to take a function like g here, right? This g can, for example, be the filter we defined previously. So it's a small function you can define, or any other function. So we take a function like g of negative tau. So we reflect that whole function via the vertical axis to the left. And then we sweep it to the right according to the time t where we evaluate the convolution, right? So we sweep the whole thing at a specific time t, we evaluate the convolution, and then we sweep that function over the other function and multiply it with that function, and build the integral of the result. So we sum up the entire multiplications while doing this sweep. And as we sweep along the right, we are multiplying these two. So here we are multiplying f and g along the sweep, and integrate that result with an infinite range, right? So to get the value of our convolution. So this is, of course, all of these functions, if they're continuous, they are defined on an infinite range. In reality, I would do it within a certain time frame probably, but basic theory has infinite support, of course. So this is also called filtering. You might have come across this with a smoothing filter in computer vision, for example, or audio, where you define a small Gaussian kernel, a small Gaussian filter, to evaluate on your input function. So this small Gaussian is your G, and your input function is your F. And in a discrete setting, you would probably integrate this as a sliding window approach, right? So your function F goes over it, and for every window, you sum and multiply these two functions in discrete value samplers, right? So some features of convolution are very similar to cross correlation for real valued functions. Okay, so it's quite different for imaginary valued functions, but for real valued functions, it differs from cross correlation only that either f of x or g of x is reflected about the y-axis. So it is a cross correlation of f and x and g of minus x, or f of minus x and g of x. So they are very, very related with each other. Now, if we look at this example from Wikipedia, this is exactly what we did with our neural network. We sweep that red g here from the left to the right. Now we multiply these functions and integrate the result. Then we get a function like this, here our activation function. And this really works for any sort of function. And now you might ask, why wouldn't I use just the input as our output signal in our very, very simplistic click detector? Well, real-world signals don't look that easy, like a click. A real-world signal might look like this here, and a real-world feature might look like this. And this is really, really hard to handcraft, right? If you're more interested in that, look into wavelet theory. So wavelets have been the bread and butter of computer vision for many, many years before the deep learning revolution. And there it's all about how to define these features, these G functions, to represent, for example, images. And if you want to know more about convolutions, there's a really good video on YouTube defining what convolution means, going all the way to Laplace transformations, and building proofs of what convolutions in this context actually mean. So for the sake of completeness, convolution acts like any other mathematical operator. The rules of commutativity are true, so convolution commutes. F convoluted with G is the same as G convoluted with F. Associativity is true. F convoluted with G convoluted H is the same as F and G first and then H. Distributivity is true, so I can do F convoluted with the sum of G and H is the same as F convoluted with G plus G convoluted with H. Associativity with scalar multiplication works as well. If I multiply a scalar to the convolution of F and G, it's the same as I would multiply A first to F and then convolve with G. So what do we learn from this? Well, A, weight sharing is the key factor for deep learning. It reduces the number of parameters from n squared in our multi-layer perceptron, for example, to really a small number. For example, 3 as in our experiment, or say a 3 by 3 filter kernel or similar for image analysis. And B, these filter kernels can be learned through backpropagation exactly the same way as you would train a multi-layer perceptron. each layer may have many filter kernels, so it will produce many filtered versions of your input with different filter functions, and these can then again be linked to a layer with many of these filter functions, so that the filter kernels are learned to fulfill a specific task. And C, for real valued functions of a continuous or discrete variable, convolution differs from cross correlation only in that either f of x or g of x is reflected about the y-axis. So convolution is a cross correlation of f of x and g of minus x, or f of minus x and g of x.